Okay, we have 3.5. Okay, we're going through proofs today. So 3.5. Okay, so 3.5 is on proof by contrapositive. Oops. Okay, so 3.5 proof by contrapositive. Okay. Okay. So proof by contrapositive. Okay. Proves a conditional theorem of the form. Theorem of the form. P goes to C. P implies C by showing the contrapositive is true. Not P, or sorry, it's not P, it's not Q. Not Q implies not P, period. Okay. Not C is assumed. Oh, it's not Q, it's C. I'm sorry. C, sorry. Okay, not C is assumed to be true. And not P is proven true. Okay, not P is proven true. Okay, let's do an example. Example 1. Okay, prove the theorem by contrapositive. Okay, prove the theorem by contrapositive. I think it's my mouse. Oh, there it is. Okay, theorem. That's true. Go away. Go away. The heck, dude? Stop. Okay, they won't be doing that. Okay, theorem. Okay, the theorem. For every integer n, or n, integer m, nope, not that one. N, was a Nancy. If n squared is odd, then n is odd. N is odd. Okay, so we want to prove this by contrapositive. So the proof is to assume the opposite of the conclusion. We're going to assume that n is an even integer and see if we get an even integer for n squared. Okay. So proof. Assume n is an even integer. Okay, assume n is an even integer. Okay, comma. Then okay, n equals 2k. For some integer k. Okay. Plugging in 2k into n squared gives n squared equal 2k squared, which is equal to 4k squared, which is equal to 2 times 2k squared. Okay. And so therefore, since k was an integer, 2k is also an integer. Since, or 2k squared is also an integer. Since k was an integer, then 2k squared is also an integer. Therefore, we can conclude that n squared is even. Okay, since it's 2 times an integer. Okay. We'll just say 2m, since it is 2 times 2k squared, or 2 times an integer. Okay. Since n being even, since n even implies n squared even, okay, or not q implies not p, then we can conclude that if n squared is odd, n is also odd. Okay. P implies Q. Okay. End of proof. Okay. Well, we should say what did we prove before we end the proof? Okay. I mean, basically that's what we proved. We proved that if n squared is odd, then n is also odd. Okay. Proof by contrapositive. I guess we can end it there because we don't really need the therefore, because we just stated it. We just stated the therefore right here. That's the therefore. Okay. That's what we're trying to prove. Okay. And so we can end the proof there. Okay. Okay, what's an irrational number? Okay, just to review. Okay, an irrational number okay, is a number that is not rational. Okay, that is a number that cannot be expressed as a fraction. Okay. The other thing we need to know is that a number is either rational or irrational. Okay. So it's either rational or irrational. So when we get this dichotomy of things where if it's not one, it's the other, then we can use proof by contrapositive. Because it's if it's not one, it's you have to have the complement, of an item. And so if we can prove that the complement is true in the opposite direction, then we can prove that the original statement is true. Okay, that's proof by contrapositive. Okay, example 2. Okay, so example 2. Okay, for every prove the theorem. Okay, prove the theorem by contrapositive. Okay, what's the theorem? Okay, the theorem is for every positive real number R, okay, if R is irrational, okay, if R is irrational, then the square root of R is irrational. Okay, so let's prove the contrapositive is true. Okay, let R be a positive real number. Okay, let R be a positive real number. such that the square root of r is not irrational. Okay, thus it is rational. Is not irrational. Okay, remember not Q. Okay. Okay. We'll prove that R is not irrational. Not P. Okay, since R is a positive real number, since R is a positive real number, the square root of R is a real number. Okay. Every real number is either rational or irrational. Is either rational or irrational. Therefore, since the square root of R is rational, the square root of R must equal some x over y for two integers x and y. Okay, if it's rational, then if the square root of R is rational, then we have to have some x and y for two integers where x is over y. Okay, and y cannot equal 0. Okay, squaring both sides it gives the square root of R squared equals x over y squared. Okay, which R would then be equal to x squared over y squared. Okay. And the square of an integer is an integer. So that's a thing. Okay, so if x is an integer, then x squared is an integer. Okay. If y is an integer, then y squared is an integer. Since x and y are integers, then x squared and y squared are also integers. Okay. 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 Since y cannot equal 0, then y squared cannot equal 0. Okay. R is then equal, it is then equal to the ratio of two integers. Two integers. And is therefore rational and not irrational. Okay, so not P. We've proven the contrapositive is correct. That not Q implies not P. Okay. Therefore, the original statement is also correct by the rules of logic. If the contrapositive is correct, then the original hypothesis and conclusion are also correct. So therefore, okay, since the square root of r is rational, implies r is rational, then the contrapositive of that statement must be true, which is if the square root of r is irrational, then r is also irrational. I think I wrote that backwards. Yeah, I'm sorry. It should be the square, this should be the square root. And this should just be r. There we go. Because it's got to be backwards. Okay, backwards in logic and backwards in direction. Okay, and that's the end of the proof. Okay, let's keep going. Okay. De Morgan's laws in proofs. Okay. Okay, A and B is false. If and only if A is false or B is false. A is false or B is false. Okay, A or B is false. If and only if A is false and B is false. Okay, example 3. Okay, it says, what would the starting assumption be? What is the starting assumption? What is the starting assumption in the proof by contrapositive? Okay, what is the starting assumption in the proof by contrapositive? Okay, so if we had a theorem, okay, if x is less than 0 and xy is greater than 0, then y is less than 0. Okay, so what would the starting assumption be here? Okay, well, we have to get the opposite of these statements. So we have an and statement, and so we want to get the opposite direction and the opposite, and we want to negate them as well. So what are we doing? We're going to take, okay, and I want to negate y is less than 0 implies the negation of x is less than 0 and xy is greater than 0. So the negation of y is less than 0 is we want to start with y is okay greater than or equal to 0. Could it equal 0? I don't think so because we're saying that the product, I don't think it can equal 0. I think then in this case the negation would normally be greater than or equal to 0, but we have to test whether or not 0 could even be a case. And because we're trying to prove something like this, okay, I don't think it's we can't have zero. Otherwise, you would get it equal to zero, and it's not allowing us to be equal. So I think we're going to have strict inequalities on this one. So it's going to be, okay, y is greater than zero. We would assume y is greater than zero. That would be my starting assumption. And what would we want to prove? We would want to prove, okay, using De Morgan's laws, that x is, okay, if we were to distribute the negation here, it would be the negation of x is less than zero, or the negation of xy is greater than zero. Okay, so this would be x is greater than zero, or okay, or xy is less than zero. Yeah, because we started with an and we go to an or. Yeah. Okay, so we would want to prove this thing in our proof. Okay. Okay, proofs with multiple hypotheses. Okay, proofs with multiple hypotheses. Okay, if H1 and H2 then C. If we have hypothesis 1, and hypothesis 2, then we get some sort of conclusion. Okay? So logically symbolizing this, we can say H1, uh, conjunction with H2, implies C. Okay, the contrapositive of this statement is not C, implies not H1 and H2. Okay. Okay, using De Morgan's laws, oops, okay, we can say that this is going to be not H1, okay, or not H2, okay. Okay, so not C implies that thing there, so let me move that over. Not C implies that guy there. Mhm. Okay, via a truth table, we could actually say that this is logically equivalent, okay, to not C and H1 implies not H2. Okay, and that's via truth table. Okay, this guy here was De Morgan's laws. Okay, so that's via truth table. Okay, so we can. Okay, using this form can make the proof easier. Okay, using this form can make the proof easier. Okay, example 4. Okay, prove the following theorem.
Professor, I just had a question for the previous problem. I don't know
Yeah.
if you addressed this, but the truth table, like justification, in our homework or exam, would we have to show the table to be able to say to
Yes.
prove the equivalency?
Yes.
Okay.
Yes. Good question. Yeah,
Can
you'd have to do the truth table unless it was something already um previously proven in either the notes or in the book. If it was previously proven, you wouldn't have to show it again. Like any of the laws that we've covered so far. Okay. But this we haven't covered already, and therefore you would have to say, yeah, you'd have to the justification would be you'd put on the side, you'd say H1, H2, and then C, and then you'd have to show via truth table that they end up being identical.
well, can we also use the conditional identities for H1 to H2, or is it because we're trying to prove it?
We're gonna use this form, okay, this form here to make things easier on our lives. So you can use this form here, you can use this forever and not prove it because I've already told you that it's true.
I see. I see.
Okay. So this is a freebie. This is up for grabs now. And anything else that we've shown is logically equivalent. Those are all up for grabs too. Okay, but this has not been shown previously in the book that these are true. I just don't want to waste the time going through the truth table to be able to utilize it. Okay. It'd be a good exercise for you to do on the side if convince yourself that this is true. Okay. Okay, but we're gonna utilize this to prove the okay, prove the next theorem. So it says not the conclusion and the first hypothesis implies not the second hypothesis. If x is a rational number, and y is a rational number, or sorry, and y is an irrational number, okay, then x plus y is irrational. Okay, so let's just figure out what we have here. X1 or H1 is that x is rational. H2 is that y is irrational. And the conclusion is that x plus y is irrational. So again, we want to prove not C implies not H1 and H2. But in this case, the easier proof is going to be to prove that not C and H1 implies not H2. And since they're logically equivalent, then we can actually say it's a proof by contradiction. Okay, because we would go back one more step in our logic. We're going to go from here back to this step, which says that we've set it up as a proof by positive. And then we would go back one more step, which would say that, well, it's just H1 and H2, okay, implies C. So, oh, okay, so, okay, so we're wanting to use this to prove this to prove the original conjecture, which is that if x is rational and y is irrational, then x plus y is irrational. And we set up the proof by proof by contrapositive, and then we can say, well, that's going to be the same as proving not C. Okay, so we can say, well, okay, not C, we're going to assume. Okay, assume that x plus y is rational. And H1, which is x is rational. Okay, and we're going to prove that y is rational. Okay, that y would have to be rational. Right? We would then prove and this is the same as saying that if x is rational and y is irrational, then x plus y is irrational. So in this case, we can get everything rational, see what the relationship is, see if that holds. Okay, and so let's see if this works for proof. Okay, let x and x plus y be rational numbers. Let x and x plus y be rational numbers. Okay. Then x plus y minus x equals y. Okay. And since the subtraction of two rational numbers is a rational number, okay, uh, okay, y must be rational. Okay. So we're saying that this thing is rational. We're saying that x is rational. And we're implying that this thing is also rational. So we can just subtract off the x. Okay. 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 Since the subtraction of two rational numbers is a rational number, then y is rational. Okay, thus this is logically equivalent to x plus y is rational. Mhm. So logically equivalent to what we're trying to prove, that if, okay, if not C, okay, not, what are we trying to prove? We're trying to prove that not C, okay, we're trying to get this next step here. Okay, that not C, and C was that X is irrational. Or no, X plus Y, sorry, X plus Y is irrational. Okay, so we're saying that therefore, going back to this step, if X plus Y is rational, then, okay, that implies that what? That implies that X and Y, okay, uh, X and Y are rational. Thus, this is logically equivalent to x plus y is rational implies that okay, x and y are both rational. Okay, and this is equivalent to what we're trying to prove. Which is that if x is rational, and y is irrational, then x plus y is irrational. We can end the proof there. Okay. And that is 3.2.